All right, let's get started. So today we are going to learn about on-device training and transfer learning. So how do we locally learn new concepts on the edge devices so that we don't have to transmit the data to the cloud and also have more opportunity to customize our model and make our devices smarter and smarter. So let's first introduce the concept of transfer learning. So what is transfer learning? Basically, it's going to want to transfer the knowledge learned from one task to use to boost the performance of a related task. So it should be a related task rather than completely different task. And we want to boost the performance by reusing the model that has been previously trained on one task. And here is an example. Say previously the model is trained on the ImageNet data, 1,000 classes, 1.2 million images, and then produced a source model, okay, and then can produce the label on the source data set. So we want to transfer the knowledge by reusing the model and fine-tune on top of it. So given a new task, we call it a downstream task, and then using the downstream data, we can predict the downstream label, okay, by reusing the model and doing fine-tuning on top of it. For example, a model used to be able to learn to recognize different kinds of cars. Now we want to apply it to recognize different kinds of trucks. That's an example of transfer learning. What about on-device transfer learning? So we want to have this process happen locally on our edge devices rather than in the cloud. What is the benefit of transfer learning locally on the edge device? For example, we can continuously adapt to the data collected from the sensors. So we can customize the model. Everyone can have his or her own model for particular taste and for particular preferences. And secondly, the data doesn't have to leave the device. So you don't have to transmit the data to the cloud server. Some of them might be privacy sensitive, like the code or some enterprise data. What if you can process and train the model locally on the edge device? That's pretty exciting. But you can imagine this will be a very challenging task because edge device has limited amount of memory. And training is much more compute intensive and also memory intensive compared with inference. So we're going to learn a bunch of techniques to cope with such challenge and enable on-device learning. So here's the agenda for today. We will first talk about deep leakage from gradient to motivate on-device learning, where gradient is not always safe to share. You can leak your source data just by observing the gradient. And then we are going to talk about what is the memory bottleneck for on-device training, why it is challenging, what is the bottleneck coming from, which motivates several techniques, including tiny transfer learning, the tiny TL, proposing the bias-only update, and also the light residual learning, followed by the Sparse BP, which is the general form formulation of the light residual learning and bias-only update, which is Sparse spec. Not all layers equal. We can selectively update a subset of the layers, and for each layer, we're going to update a subset of the channels. So this is applying sparsity, and also we can apply quantization for on-device training. We're going to learn about quantized with aware scaling. So naively using the quantization techniques we learned for inference does not apply to training since the accuracy calculation is pretty huge. And we observed actually there is a little bit of math we have to play with. Once we get it solved, just a couple of lines of code using this simple quantization-aware scalar, we can scale back to make sure they converge even using 8-bit for training. And if I have time, or maybe the next lecture, we are going to learn how to achieve the measured speedup from these above techniques to convert the theoretical saving into the measured speedup. So that will be the Pocket engine, the system support for sparse backpropagation. So now let's start with the first part of the journey, deep leakage from gradients, where gradients is not safe to share. So let's first introduce federated learning. Okay, so federated learning is a very popular mechanism to only share the gradients among multiple devices, and also the weight rather than the user data. So the user's data stays local on the mobile phone. And on the right-hand side is showing a mobile app example where the Google's keyboard can benefit from multiple users' typing history and improve the model so that in the future you can have a faster typing and more smooth typing experience. And what it does is basically having a couple of steps, starting from the users generate the personal data on the edge, for example, the typing history, and perform the local training to get the weight update. And each device update its own model using the local data for a couple of iterations. It may not be just one iteration, but could be a couple of iterations. And then each device gets updated model. So those models are sent to the server. So the server will average the model coming from different devices and then send back the updated model to each device. So in this cycle, the important private user data doesn't have to leave the device. So you only transmit the gradient or the weight update. So that is the Fed average algorithm. But actually, is it safe if we share the gradient? So we want to rethink the safety of the gradient. So convolutional neural networks can get a prediction for the cat and dog and get a loss. And then different devices will derive the gradients from the training data. So you can get a gradient. And devices will gradient to update the model. But our question is, can we use the gradient, try to steal the input image? So we have the weight, we have we have the gradient. Can we steal to leak the input image by observing the gradient? So conventional wisdom basically separates the private data, the private input, versus the public data, which is the gradient or the weight update. So existing work is showing that we can try to get some input information by observing the gradient. For example, membership inference. So given the gradient, it's actually possible to find whether a data point belongs to the batch. And also the property inference. Given the gradient, it's possible to find a data point with certain property is in the batch. So by observing the gradient, we can perform this membership inference, whether a record is used in the batch or if certain property is in the batch. But can we go one step further, not only see the membership, the property, but try to steal the raw data? Okay, so gradient contains a lot of information about the training data. Can we just obtain the raw training data from the gradient? So here is an example. So we call it deep leakage attack. So we start with the input image, and we have the model, we get a prediction, we get a loss with a label, and produce the gradients. What we can do is, since we have access to that model, we can initialize a dummy input and a dummy label. It can be random input and random label. And then we feed the dummy input into the model, produce a prediction, and compare with the dummy label, we produce a loss. And then using the loss, we can calculate the gradient for the weights. What we do here is trying to match the two gradients, trying to match the gradient and calculate the MIC loss between the gradient of the original model original input, original prediction versus the dummy input and dummy label. We try to match the gradient so that we can have a loss right here by observing the difference between these two gradients. And then we can backpropagate this loss all the way to the dummy label and all the way to the dummy input. So at each iteration, we're going to update this dummy input together with the dummy label so that the gradient produced here will be closer and closer to the gradient produced by the original image and the correct label. So put it in another way, so this is the deep leakage attack via gradient matching. So we have the true input, we have a dummy input, we try to learn the true input from this dummy, randomly initialized input, and also the randomly initialized output. So both the top and the bottom model is going to produce a gradient. Okay, produce a gradient. We are trying to match the gradient by minimizing the loss. How do we minimize that? We backpropagate to this dummy input and also this dummy label. So across a couple of iterations, we are going to leak the input image by trying to match the gradient. So here only the gradients are shared between the malicious attacker and also the normal users, which both have access to original weight. But this will leak the privacy. We can steal out the data. For example, here we are trying to recover the input image. Just by a couple of iterations, by trying to match the gradient, we can steal the training data. So this is just one image, attack a vision model with batch size of 1. What if we have multiple images in the batch? Will it get the attack easier or harder in this way? So far, we are showing we have one image in the training data. We can try to leak the input data by trying to match the gradient so that this random input, random initialized input can actually get recovered the ground truth. So what about if we have multiple input images in the training batch? Is it harder to attack or is it easier to attack? So if you think about the methodology of this attack process, actually we have a couple of equations, which the number of equations equal to the number of gradients. We are trying to match the gradient, right? So that gives you many equations. What are the variables? The variable is actually each pixel, which we are going to solve. So you have a fixed amount of equations, but if you have a larger amount of batches, you have more variables to solve in that equation, right? So it's going to get harder. Sometimes multiple variable will lead to the same result. But so far here, we can find with 6 or 7 images, we can still steal it really well. After a couple of iterations, we can get the monkey, we can get the bicycle. The order gets changed, but the content really stays the same. So this is with larger batches. And also it works well not only for vision tasks, but also we can attack a language model. So here we show the result on BERT. We learn about BERT is a mask language model. So at iteration 0 is going to say a tiling field given less word something fine. It's not correct. It's random initialized. After 20 iterations, it's somehow getting correct, like registration, volunteer application at student level, travel application open the week of played. It still contains some error. But after 30 iterations, it's going to say like iteration, volunteer application, and still travel applications open the first week of September. It's already pretty close to the original text. So here we can try to attack not only images, but also languages. What's the limitation here? We can see the pixel resolution is actually pretty low in the CIFAR dataset. This is again due to we have a fixed amount of equations, which is trying to match the gradient. The amount of information you have is equal to the dimension of the gradient, which is equal to fixed amount. But if you want to steal more data, that's going to be harder. So far here it works on relatively low resolution images. It's getting large. If you're trying to steal information from a large language model or vision language model, where you have so many equations you are trying to match, so you have more information than the equation. So that is trying to help you understand deeper. How do we define that? Is there a way to define the leakage? Trying to prevent it from being the information from being stolen. We can add noise, very natural way. We can either add Gaussian noise or Laplacian noise. So adding Gaussian noise, as you can see, the more noise we add, the lower the accuracy. And also here, if you add a little bit of noise, it's still going to leak the information. If the Gaussian noise strength is not big enough, like 10 to the -4, 10 to the -3. But when there's no leakage, the Gaussian noise has to be pretty large. When the Gaussian noise is large, the accuracy of the model is less than 1%. So the model is not barely usable. So adding noise is not a good solution. When you can protect it from being attacked, the accuracy almost goes to 0. Actually, gradient compression can solve this issue. As we can see here, when we prune a couple of gradients, like pruning 1%, still there is deep leakage. This is recovering the tree. 10% still, this is the gradient match loss. You can still somehow leak the input image. When it goes to like 70%, which we talk about gradient compression, what was the pruning ratio we can achieve without losing accuracy? It's more than 99%, right? So there's plenty of room to prune those gradients. So 70% is very doable. And at 70% gradient pruning ratio, the accuracy is actually very well maintained. Like we can easily prune it to a pretty heavily without losing accuracy. And why gradient compression, gradient pruning helps to prevent this deep leakage? Right, so you have less information, less equations, less things try to match. They're both 0, so you don't actually know how do we match it. Right, so the number of equation equal to the number of gradients. If you have less number of gradient that is non-zero, you have less number of equation to solve.
The attacker knows that you're trying to
so it may not know whether, so if it observe a 0 gradient, it may not know whether it's pruned to 0 or it's initialized or it should be 0. That's why it has less information to try to steal from. So actually the implementation is super simple, just about 20 lines of PyTorch implementation. You're just trying to match the gradient and trying to backpropagate to the dummy input and also the dummy output. A lot of citations in 2019. Okay, so hopefully that motivates us the importance of on-device training, where shouldn't try to share the gradient. Sharing the gradient can potentially leak your training data. So we want to stay local. Everything stays local. But it's not easy. We're going to analyze the memory bottleneck of on-device training. From cloud AI to mobile AI, the compute resource and also the memory is a lot smaller, especially the memory. This is the NVIDIA H200 DGX server, which was released yesterday. It has 141 gigabyte of GPU memory for each card, which is pretty exciting. A lot larger than the previous H100, which was 80 gigabyte. For mobile device, we can easily have like 4 gigabyte of memory, 256 gigabyte of storage of flash. But as we learned in the MCUNet class, Tiny AI for IoT devices, you are limited to a couple of 100 kilobytes of SRAM and maybe 1 or 2 megabytes of flash. So that's several orders of magnitude smaller. So we want to reduce both the weight and activations so that we can fit the deep neural nets to perform on-device training. The motivation is very similar to inference, but it's more challenging since we have more things to take care of. So this is for inference. This is for training with batch size of 8. We compare the memory consumption. Actually, it's a lot larger. So about 20 megabytes needed for inference, about 452 megabytes needed for training. And this is the memory constraint for a Raspberry Pi 1. The DRAM has 256 megabytes. The microcontroller has even smaller memory. So edge devices has tight memory constraint, and the training memory footprint of neural nets can easily exceed such limit. And let's try to analyze why training memory is much larger than the inference, especially for CNNs. So the answer is due to those intermediate activations. Remember the chain rule. When we are doing the forward, we calculated layer by layer. Unless we use the patch-based inference, usually we do it layer by layer. After computing one layer, the activation of that layer could be thrown away, and you can move forward to the next layer. Unlike inference, in the backward, when we are trying to calculate the gradient to the weight, the activation of that layer is needed. So we have to store the activation during the forward pass so that in the backward pass, when we are trying to calculate the gradient to the weight, that activation will be used. So we have to store the activation in order to calculate the gradient of the weight. So inference does not need to store all the activations, but training does. And activations also grow linearly with the batch size if you want to do batch the training. But for inference, on the edge, the batch size is 1. And even with training with batch size of 1, if you want to use other like fat average or gradient accumulation with batch size of 1, activations are beyond the limit of many edge devices. And also edge devices are energy constrained because they are battery constrained. So if we can fit them into the on-chip SRAM or you fit in the cache, that would be pretty good. Actually, that's the case for both the edge and also the cloud. So what is the memory bottleneck? And the answer is the activation. Okay? So we try to see from different neural net models from Resident 50, this is the amount of parameters, this is the amount of the activation. Actually, the activation is actually a lot larger than the weight. In the next lecture, we are going to switch gear to talk about large language model fine-tuning. The conclusion is actually different. For large language model, the parameter is more than the activation using reasonable batch size. What about switching to MobileNet? Remember we talked about MobileNet, which is very flop and parameter efficient for inference on the phone. So we plotted the parameters of MobileNet. Indeed, you get like 4x smaller amount of parameters. But the main bottleneck, which is the activation, only improved by about 10%. So the main bottleneck did not improve much from ResNet to MobileNet for training. And why is that the case? Because MobileNet focuses on reducing the number of parameters or the flops. Okay, so the major change is that introduced this depth-wise convolution. In order to compensate for the loss of capacity using depth-wise convolution, it has a pretty big expansion ratio, usually 6. So the number of channels gets expanded by 6 times. So you can imagine H by W by C. The C is 6 times larger. The activation is actually much larger. But that doesn't hurt the flops or hurt the parameter. We can still make it parameter efficient, since stepwise convolution is just 3 by 3 by C. That's the total number of parameters, rather than 3 by 3 by C in by C out. It has one less dimension and certainly has fewer number of parameters. Similar strategy for the flops, but the activation suffered in this way. So the main bottleneck, which is the activation for CNNs, does not improve much. What about some efficient fine-tuning techniques? Can we try to save the memory by only fine-tune the last layer? Okay? Only fine-tune the last classifier head. That is pretty efficient, as we can see. This is showing the number of trainable parameters reduced by a lot. But the drawback is that there's significant accuracy degradation. So this is fine-tuning the full rather than 50 versus fine-tuning only the last layer. It's very efficient, but the capacity is limited. You don't want to have such sharp degradation of the accuracy. Another approach, a very smart approach people proposed, is actually fine-tune the batch normalization layers and also the last layer. To fine-tune the model. And this is very parameter efficient. You can see the trainable parameter is reduced by 12x, since we only have to fine-tune a little bit of the parameters, the scaling factor and also the bias. And you can see the accuracy boosted pretty significantly compared with fine-tuning the last layer. It's very parameter efficient with okay accuracy. However, the batch normalization and the batch normalization tuning and also last layer tuning actually is not quite enough for on-device learning, because the parameter efficiency does not translate to the memory efficiency. So showing this figure, the number of trainable parameter is reduced by 12x. Okay, but the actual memory, training memory, is only improved by like 80%. Right? So in order to fine-tune those batch normalization layers, you still have to store a lot of activations, and those are the actual real bottleneck. So fine-tune the batch normalization layer, the parameter is very parameter efficient, but the memory saving, the measured memory saving, is limited. And also the accuracy degradation, although it's better than fine-tune the last layer, compared with full fine-tuning, is still very significant, like double-digit loss of accuracy. And how do we solve this issue, right? Try to close the accuracy gap and also have pretty significant measured memory saving. So let's talk about tiny transfer learning, okay? Tiny TL, to solve this problem. So on the top, we are showing the weight and also the activation memory denoted in different colors. Okay, so the orange, the yellow part is showing the parameters, and the green part or the blue part is showing the activation. So this is an inverted bottleneck layer, started with a 1-by-1 conv with the expansion ratio of 6. So it's from small to large number of channels. And immediately you get a 6 times C. Originally you have C by resolution. C is the number of channel. Since you have an expansion ratio of 6, the activations channel is expanded by 6 times. Pass through another depth-wise convolution, you get another 6C by R, and followed by another 1-by-1 convolution that project from 6C to C. So that's one block of the inverted bottleneck. So we try to analyze why updating the weight is memory expensive, but updating the bias is not. So what is updating the bias? We just update the bias rather than all the weights. Okay? So if you do the chain rule, this is the forward AI plus 1 equal to AI times WI for layer I plus the bias plus the BI. When we are calculating the backward, the partial loss over partial WI equal to the AI transpose times partial loss over partial A plus 1. So in order to calculate the gradient with respect to the weight, you need to store the activation here. This is the corresponding activation. But updating the biases does not. So updating the bias, the partial loss over the partial bias equal to partial loss over partial A plus 1. Okay, since this is a linear term, there's no scaling factor in front of it, and etc. Okay, so therefore, updating the weight requires storing those intermediate activations, but updating the biases does not. So updating the bias is very memory efficient. You can see if you can freeze the weight and only fine-tune the bias, we can save 12 times the memory compared with fine-tuning the batch normalization plus the last layer. But doing this method alone will hurt the accuracy. We can observe about 16% accuracy loss. So this is a good starting point, but not the final good point we are going to use. So how do we close the gap of that accuracy gap? So far, we are using a very simple bias, just one scalar value. Can we learn something more powerful and also keep the memory footprint to be low? So here we can use this new technique called light residual learning. So the bias is a kind of residual. Okay, so this is the main branch. Okay, one by one, stepwise, another one by one, and this is the residual branch. So previously we are just learning the bias. Okay, now we are having a residual that's trying to learn the bias that is learnable. Okay, we first downsample the main branch to get this bias branch, this residual branch, so half of the resolution. So since the compute grows quadratically or decreases quadratically with the resolution, so this is only 1/4 of the activation size or the flops. And you pass it through a group conv. Group conv is the efficient way to reduce the number of parameters as well as the activation size. Group conv, so you get a C by half the resolution, and then you pass it through a 1-by-1 convolution. We never expand the number of channels from C to 6C, so it remains to be low in the number of channels, remains C rather than 6C. Pass it through another 1-by-1 convolution, so we can have this upsample layer to upsample from half resolution to the full resolution. Okay, so here there's no depth-wise, there's no inverted bottleneck. Just use a group conv followed by a 1-by-1 conv. This is spatial modeling. This is channel-wise modeling. Provided some extra capacity, we can tune the yellow part. Okay, we are tuning the yellow part in the residual branch as well as in the main branch. We are only tuning the bias here, but we are not updating the main weights in the main branch. So the key principle is to keep the activation size small by first reducing the resolution from R to half R, and also avoid this inverted bottleneck. C here is also C rather than from C to 6C right here. So by avoiding inverted bottleneck, we use 1/6 of the channel compared to the main branch, half the resolution, only 2 layers rather than 3 layers on the top. So 1/6 of the channel, half the resolution, 2/3 of the depth. That's only 4. Multiply them all together. It's only 4% of the activation size. Pretty small overhead, but add enough capacity to recover the accuracy. See here, only 5 megabytes of memory overhead compared with like 400, and improved the accuracy by like 11%, which is pretty significant. Adding an extra little bit of capacity by introducing this residual branch and drastically improve the accuracy with little memory cost. So this is our figure before. Previously, we have this 12% gap by using Google's batch normalization layer learning method, just trying to learn the batch normalization. There's 12% gap. Now, using TinyTL with light residual learning, we can close the accuracy gap. And here, previously, there's very limited measured memory saving. Since fine-tuning the bias, fine-tuning the batch normalization, still need to store all the activations. By here, using TinyTL by light residual learning, we can have 6x measured memory saving. Actually, there could be another approach. So we talk about this once-for-all network, which we did in lab 3, where we can train a super network that can contain many subnetworks. Imagine if we have a difficult data set, we can use a larger subnetwork from that once-for-all network. Okay? If we have a mid difficulty, we can use a mid subset. If we have an easy data set, an easy downstream task, like just classifying hand digits, we can use a much smaller subnet. So we can use specialized subnetworks to deal with different downstream tasks. Okay? So specialization is a very key technique in computer architecture, where specialization usually need to lead to higher efficiency. But here, for different tasks, we can also specialize the deep learning model to cater for different difficulty levels of difficulty for different downstream tasks. Another interesting finding is that a model that performs well on the ImageNet may not perform well on the downstream task. Could you take a look? It doesn't work. May not perform well on the downstream task. For example, this is the accuracy about MobileNet v2 rather than 34, Inception v3 rather than 101, everything together. The relative accuracy, the sequence actually is different. For example, the Inception v3 is having pretty good accuracy right here on the ImageNet, but Inception v3 may not be the best performing model on the flowers dataset. Similarly, if you see the best performing model on the flowers, which is less than 50, but is not quite performing super, it's actually number 3 on the ImageNet. Okay, so the relative accuracy order between different pre-trained models change very significantly among ImageNet and other transfer learning datasets, such as cars, flowers, aircrafts, okay, which motivates this kind of personalized and also specialized neural network architectures for different downstream tasks. Well, this is the slide from last year. This year, the landscape has changed. We will not have a single foundation model to deal with different downstream tasks without having to fine-tune the model. So this is called zero-shot or few-shot learning, which is pretty exciting, actually. The next lecture, we are going to talk about several techniques like prompt tuning or p-tuning. Without having to change the model, you can deal with different tasks. Let's go back. So TinyTL up to 6.5 memory saving in this way. Okay, this is on the flowers, cars, and also food, different data sets. So here we have the fine-tuned BN plus the last. This is fine-tuned the last layer only. And here we are fine-tuning the full network. Okay. So compared with fine-tuning the full network, this is the memory versus accuracy trade-off. Okay, we can save about 4.5x the memory across different benchmarks. How about activation pruning? Remember, we talked about the activation is the bottleneck for the training memory for scenes. So we can also compare with pruning the activations. Okay, so this is pruning the Ryzen 50. This is pruning the activation of MobileNet v2. But actually, TinyTL is actually surpassing these different techniques by using this light residual learning and also using the bias-only update. Actually, the light residual learning it's very similar to the later technique called LoRa, which we learned to fine-tune language models. Just use a very lightweighted residual branch to add the capacity without adding too much memory. So TinyTL enables purely in-memory training, so we can push this frontier of the memory size by maintaining accuracy to only below 16 megabytes, which can easily fit in the on-chip SRAM in the cache. So TinyTL support batch 1 training by group normalization. So by using group normalization, even with batch size of 1, we can still converge pretty well. And together with the light residual model, can further reduce the training memory to 16 megabytes to fit the L3 cache very easily. Sometimes it can go to 128 megabytes these days for AMD CPUs for L3 cache. So we can fit the training process into a cache, which is much more energy efficient than training in the DRAM. All right, now let's take a break before we dive into the sparse backpropagation. Okay, welcome back. Let's talk about sparse backpropagation. So previously we talked about this dense backpropagation, where in order to calculate the gradient of the weight, we need to store all the activations. In order to calculate the gradient of the activation, we need to store the weight. So we need to store a lot of activations if we need to backpropagate all the way to the beginning layer. So the inference does not need to store those activations because you can throw them away after the next layer, but training does. And the activation grows linearly with the batch size. So if we can prune some of the layers, we can actually save the computation, not only save the computation, but also save the memory, not have to store those activations if we don't need to calculate the gradient of that layer's weight. Actually, such kind of sparse learning exists in the human brain. This is a very interesting study where a newborn child has about 2,500 synapses per neuron, and then this number surges to 15,000 synapses per neuron when the child grows to 2 to 4 years old. During adolescence, which is actually the K-12 education happens, the number of synapses are getting sparser. Okay? It didn't increase, but actually decreased during this adolescence time, where we are learning most of the knowledge in our lifetime during this K-12 education until it gets stable, which indicates that certain kind of sparsity might be helpful for learning. Fine-tuning the last layer is a special case for sparse learning. It's so sparse where we are just learning the last layer only. It's very cheap, no need to backpropagate to the previous layers, but the accuracy drops very significantly, although the trainable parameter also drops. The bias-only fine-tune can also be thought of a special case of sparse learning. We are not learning the main weights, but only the biases. So for each layer, we don't need to store those activations, since calculating the bias, unlike calculating the weight, does not need to store the activations. There is still a performance gap using this way, although the memory cost is much smaller compared with full fine-tune and very comparable to fine-tune the last layer. It's actually superior to fine-tune the last layer because it almost adds no extra memory compared with fine-tune last, but improves the accuracy a lot. Very low hanging fruit. And the general approach is to select those layers that are not contributing much to the backpropagation, to the learning process. For example, sparse layer backpropagation is saying that some layers are not important as others. For example, this layer may not be as important, so we don't need to update the weights. And some channels within a layer may not be as important, so we can prune away those channels within a layer. And usually we don't need to backpropagate to the very beginning, to the very first layer, because those layers are usually learning some of the low-level features, which might be the same for different tasks, like different concepts in the low level. So we may as well freeze those layers and only fine-tune certain late layers. This can also save the memory, since once the backpropagation stops here, we don't need to store any of the activation before that. And we only need to store and compute a subset of the activations. So previously, we need to calculate the dy over dw. This is the G transpose times the activation. This is flowing from the previous layer. This is the current activation. In order to compute dw, we need to store the activation. If we need to compute only partial update for that particular layer, we only need to store partial activations, which can, in this case, we are saving 3/4 of the activation, since here we are only update 1/4 of the weight. So we need to store only 1/4 of the corresponding activation. The next question is, how do we automatically find which layers are salient and which channels are salient? So this is putting everything together. Dense, full update, full backpropagation, last layer only backpropagation, bias only backpropagation versus sparse layer, sparse tensor backpropagation. And this figure shows the trade-off between the memory consumption versus the accuracy contribution. And on the top, it's showing two colors, the yellow for the activation and also the blue for the weight. For CNN, we can find the first couple of layers are dominated by activation. Every activation is pretty big. And for the later layer, the weight is actually pretty big. Why is that the case? In the middle, the memory is actually smaller. The reason is that in the beginning couple of layers, the resolution is large. And then as you do downsample, the resolution gets smaller. And the size grows or decreases quadratically with the resolution. So as you downsample, the activation quickly shrinks. What about the weight? In deeper layer, usually you have a larger amount of channels. So the weight size actually is getting larger. So the sweet spot is in the middle. So actually, our policy decided to learn several layers in the middle. Okay? Sparse layer update. And also sparse tensor update in the several late layers to contribute to the accuracy. So these are some of the opportunity where we can put it in a big design space, but consider both the size of the activation, size of the weight, and also the accuracy contribution. Not only the contribution, but also the cost. So contribution analysis is basically saying which layer is contributing more to the update, which layer is not contributing much. So contribution analysis basically says we want to fine-tune only one layer on the downstream task and measure the accuracy improvement, the data accuracy, as the contribution. And when we are fine-tuning, we only fine-tune the layers with a high delta accuracy, which means that layer is contributing more to the final performance. So we plotted very typical layers, one in MobileNet v2, the other in BERT. Very interestingly, we observed very regular zigzag pattern. Okay? Low, low, high, low, low, high. Okay? Every period of 3 layers. Why is that the case? Because you have the pointwise, stepwise, pointwise. Okay, so here actually pointwise, pointwise, stepwise, pointwise, and then pointwise, stepwise, pointwise. Very interesting pattern. So which layer should we fine tune? Which one is not? Should we not? This is the contribution, the delta accuracy across layer 0 to layer 40. Some of the layers are contributing more. Some early layers are actually contributing negatively if you fine tune them. The last layer here is actually contributing a lot. So we should fine tune those layers, right? Those layers whose contributing is more. And actually the first depth-wise layer, which is this one, and also this one, every 3 points, okay, every 1, 2, 3, 1, 2, 3, 1, 2, 3, every 3 points, we have this first point-wise layer. Why do we need to fine tune that? First reason is they contribute a lot, like more than 5% to the final accuracy. Of course, assuming they are independent. Actually, it's not, but this is a good approximation. Accuracy contribution. Secondly, the input activation size is small because this is one channel. This is a channel dimension of C. This is 6C. So here you have to only store 1C, but if you want to fine tune these two layers, you have to store 6C due to the large expansion ratio size of 6. So fine-tuning the first point-wise layer is very efficient. Both it's contributing more and it's having a smaller cost for the activation. And let's visit transformers, where we have this QKV projection, multi-head attention, output projection, followed by two FFN layers. So what are the learnable parameters? We have QKV, okay, three matrices. Multi-head attention doesn't have any weights, so nothing to fine-tune here. Output projection, so 1, 2, 3, 4, 5, 6, 6 layers. And again, we find this very regular repeated pattern of 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. Okay? Every 6 point, you have a periodic pattern where the QKV projection is contributing pretty significantly. And then this output projection is not contributing much. It's on the bottom. FFN1 is contributing more to the FFN2. Similar here, QKV contributing a lot, output contributing not much, FFN1 contributing more than FFN2. So in this case, so for transformers, we should just fine tune this QKV projection and also the first linear layer. Actually, this is also very cost efficient because this FFN layer has this inverted bottleneck structure where we have one channel, there's a 4 channels, expansion ratio of more than 1, roughly between 2 to 4. Okay, so actually the activation size here is smaller than here. So the number of activation you need to store if you want to fine tune FFN1 is actually less than FFN2. And accuracy contribution is actually more for FFN1 in this case compared with FFN2. And that's consistent across different layers. So in summary, different models prefer different layers for fine-tuning. You want to do such profiling once and then apply it to different downstream tasks. So Mobile V2 prefers the first depth-wise conv to be fine-tuned. It's contributing more to the accuracy and also it's taking a smaller amount of activation. The cost is also small. And BERT prefers this QKV projection and also the first FFN layer to be fine-tuned. And within a certain layer, we can also fine-tune different portions of that layer, like fine-tuning all the channels, half of the channels, 1/4 of the channels, or even 1/8 of the channels. You can imagine the more you fine-tune, the higher the accuracy you get. So we can do this profiling only once on a particular data set so that we can automatically search given a budget, given a memory budget, okay, fine-tuning the ith layer with ratio R with the with the bias only update, with k layers of bias only update, the memory consumption should be smaller than a given constraint. If you increase k, certainly you have better accuracy, but you have larger memory as well, similar for I and R. So this is, you have to satisfy this constraint. And here we try to maximize the accuracy contribution, okay, by fine-tuning which bias to fine-tune, like last k layer, where do we stop last k layer, and which index of the layers we want to fine-tune the weights, and what is the ratio for the channel. Okay, ratio 100%, half, 1/4, and 1/8. We want to maximize the contribution coming from those bias only update all the way up to layer K, and also the delta accuracy, the accuracy contribution by updating layer I with ratio R. So we can use this model, plug it in to the evolutionary search. Compared with random search, evolutionary can very fast, can very quickly get a very good accuracy without searching too many epochs. Thus, we can train the model on the edge with low memory cost and also achieving high accuracy. This is showing the accuracy comparison on DistillBERT, BERT, MCUNet, MobileNet v2, ResNet 50, comparing this is the full backpropagation. This is bias only, it hurt the accuracy, but sparse BP, by smartly selecting the sublayers, we can overcome the accuracy loss. Very, very comparable accuracy, sometimes even a little bit better compared with the baseline model. So sparse BP demonstrates on par similar performance compared with full BP on both vision and also language tasks. So that we can deploy the microcontroller. So this is the measure result about the actual memory required for deploying MCUNet, MobileNet v2 with multiplier with 0.35, Proximity NAS with multiplier 0.3. So comparing update the this is updating the last K layers, including updating last other layers. Okay, this is the best upper bound versus updating the bias only, very small memory compared with those, but accuracy is also low. While sparse update can get the best of both worlds, having a much better trade-off, so low memory footprint but high accuracy. Actually, it can get higher accuracy compared with updating the full model or updating last K layers with 4.5x smaller memory, but even more accurate. It can fit within like 150 kilobytes. Not only those tiny models, but also those large language models, we can fine-tune them on edge device like Jetson Orin. So the model we tested here is the Llama v2, 7 billion parameter Llama v2, and fine-tune it on the Stanford Alpaca dataset, which has 52 instructions. We're performing instruction tuning to align the model with human instruction. And here are several examples from the Stanford Alpaca dataset. For example, what's the meaning of the following idiom? And the input is, it's raining cats and dogs. And the output should be, the idiom, it's raining cats and dogs, means that it's raining heavily. Another instruction, translate the following phrase into French, and then it's translating the input to the French. So those are some of the examples. Those kind of instructions are trying to equip the large language model with the interaction ability by providing some examples. Although most of the knowledge and capabilities are learned during pre-training, this kind of instruction tuning and also called alignment is pretty crucial to teaching the LLM how to interact with the users. And let's see how does sparse fine-tune improve the speed and maintain the accuracy. So there are several frameworks using PyTorch versus using POC engine, our fine-tuning infrastructure. Compared with full fine-tune, sparse fine-tune is like 2x faster and a lot faster than the PyTorch baseline due to the efficient POC engine on Jetson Orin. The memory is comparable to using the LoRa approach, but it's a lot faster, like 7 seconds versus 0.9 seconds. And the Alpaca evaluation win rate is on par, sometimes even better compared with LoRa fine-tune or the full fine-tune. And here are some fun examples about sparse backpropagation, about fine-tuning large language model on device. We do some qualitative analysis. The input is, what is the capital of the United States? The original Llama 7B is saying Washington, D.C. Full backpropagation also answered correctly. Sparse BP also answered correctly. So for simple questions, our models actually consistently deliver pretty accurate response. On the right-hand side, what is Michael Jackson's last album? The original model says he passed away 2020, and the last album is Michael Jackson, The Ultimate Collection. Actually, is not correct. Well, the fine-tuned full backpropagation fine-tuned model can correctly answer is invincible, and fine-tuned with sparse backpropagation can also say released during his lifetime was invincible, which was released in 2021, not 21. So for obscure questions, the original Llama model no longer provide good answers, while the sparse BP can pretty much match the accuracy with the full BP. We can also try it with some reasoning task. For example, the micro conference was running virtually online in 2021, physically Chicago in 2022, and will be in Toronto in 2023, actually 2 weeks ago. Now is the year of 2023. Where was Chicago micro hosted last year? We'll do some reasoning. Last year is 2022, so it should be in Chicago. Well, the Llama V2 original says micro was hosted virtually in 2021. Didn't get correctly like last year of 2023. It should be 2022. But the fine-tuned model with full BP answered it correctly. With sparse BP also answered it correctly. Another interesting example, please reverse the words in the sentence. I love the micro conference. The reverse should be conference micro the love I, but without instruction tuning. It says I hate the conference micro. Completely wrong. While the full BP says the reverse result is conference micro the love I is correct. While the sparse BP fine-tuned model says conference the micro love I, conference the and micro is actually messed it up. It's showing that the sparse BP sometimes still have the limitation compared with the full BP. But this is just cherry pick. Probably on average, it won't be that bad. And we can also challenge it with some math task, compare the full BP versus sparse BP and without BP. So here, Lee mows one lawn, charges $33. He mowed 13 lawns. 3 customers each paid $10 of tip. And how much did he earn last week? So it should be, actually the original model says 660 is wrong. But the full BP fine-tuned model can calculate 33 times 16 plus the tips, $30 of tips, add them up together, you get 558, which is correct. And sparse BP is giving a very long answer here. So it's giving the whole process. What is the thought process? Like each one is 33, and he mowed 16 lawns and $10 tip, and calculate the total number of tips. So you can calculate them together by multiplying with 16. Add them together, you get 558, which is pretty good. So basically saying that sparse BP is very good at handling this language fine-tuning task compared with the baseline full BP methods. Question?
Is there like a qualitative reason why the answer is a lot shorter?
Yeah, we observe the same issue here. Haven't have a like theoretical analysis. Why is it the case? Similarly for this case, this is slightly more concise for the BPP, while the sparse BP is giving more process. It can be either good or bad. Good because you can have better thought process. Bad because it can take longer to generate more tokens. All right, so we talk about sparse fine-tuning. Can we exploit quantization for fine-tuning tasks? So now let's switch gear to talk about quantized training with quantization-aware scaling, QAS. Remember, we talk about quantization rather than having a full precision training with 32-bit. Can we use quantized training with low precision? So this is the real quantization graph. We have the input, we have the weight. Using quantized approach, we do the convolution in int8. The result is accumulated in int32. We add a bias, which is also in 32. We scale it with a scaling factor, and then we can quantize again to feed to the next layer. This is very efficient. You have 4x less bit width compared with FP32, but it's difficult to update. So there's a related work called fake quantization, which we introduced earlier during the quantization part. So fake quantization is basically saying we can convert the FP32 weight into a int8 representation. Okay? But we are still using FP32 to represent an int8 number. So this is done at training time in order to produce a good model that's good for inference. So that is part of the quantization-aware training, and the end goal is to produce a model that is suitable for int8 inference. So it doesn't save the training memory, because in the training time, everything like the convolution is still happening purely in FP32. It's using a FP32 number to represent a quantized int8 number. It cannot save the memory footprint. So real quantized graph can actually save the memory, but it's hard to quantize. So different from this fake quantization during quantization-aware training, where the input and the weight, they're actually represented with FP32. So in real quantization, both the weight and input, they are quantized and represented in int8 for inference, and also we can use that for on-device training. But this is leading to optimization difficulty, right? So previously, during inference, batch normalization can be folded into batch normalization can be folded into the previous convolution layer. But now everything IP is in int8. We no longer have that luxury to use batch normalization to do the adjustment. And as a result, using the naive int8 approach to do training can get double-digit top-line accuracy degradation due to the lack of batch normalization and also the mixed precision. So it's difficult to use int8 for training, to use a real quantized graph for training. And why is that the case? What is the mismatch that caused such optimization difficulty? So here we plotted the weight over gradient ratio. Okay, so this is log of weight over gradient. Okay, for IP, this is the IP32. This is the int8. Actually, we find the scale of the weight over gradient with IP32 versus the quantized training is drastically different. And what is the consequence of that? The weight over gradient is super small for the int8 training. Pretty large weight, pretty small gradient. So you are not learning anything. The gradient is so small to nudge the weight, right? So we need to conquer this problem. And we see this zigzag pattern for interleaved between weight and bias, weight and bias. We have this zigzag pattern. And how do we solve that problem? So let's do a little bit of math. To do the calculation, we have an 8-bit weight, 8-bit activation. We have a 32-bit bias, so the W bar is the quantized weight. And then we multiply with the scaling factor. Remember, we talked about that in the quantization class. And then we cast it back to int8 before we feed to the next layer. So for per channel scaling, the weight equal to a scaling factor times the quantized weight. The quantized weight ranges from minus 128 to plus 127 if we use 8-bit quantization. Well, the original floating point weight might be something around 1 or in that neighborhood. So if we calculate the gradient with respect to the quantized weight, we just apply the chain rule. If we know the gradient with respect to the original weight, we have SW here. So the gradient with respect to the quantized weight will be scaling factor times the original gradient to the FP32 weight. So now is the interesting part. We want to calculate the ratio between weight and gradient. Why is that important? Because we don't want the gradient to be too large, otherwise it will overwhelm the weight. We don't want the gradient to be too small, otherwise it cannot nudge the weight. Okay, we want this number to be reasonable. So this is after quantization, weight over gradient. This is before quantization. So we plug in the quantized weight. Okay, so quantized weight equal to the original weight divided by SW. Okay, original weight divided by SW. This is a gradient to the quantized weight. Gradient to the quantized weight. We plug in this equation here, which is scaling factor times the gradient to the weight. The scaling factor times the gradient to the weight. So we put them together. We can see the term SW appeared twice in the denominator. So there's actually SW to the power of -2 times the original ratio between weight and gradient. So the new weight over gradient is SW to the power of -2 of the original weight over gradient. So you immediately see this mismatch. The question is this larger than 1 or smaller than 1? The SW here. So this is the quantized weight from plus 127, and we times scaling factor projected to somewhere around 1. So this is something much smaller than 1. To the power of -2, something much larger than 1. So as a result, the new weight over gradient after quantization is much larger, something larger than 1 times the residual weight over gradient, which explained why the gradient becomes much larger. This is in log space. It's actually many orders of magnitude larger. To solve this problem is actually easy. We just scale back weight over gradient. Just a few lines, 1 or 2 lines of code. So we create a new gradient over weight equal to the original gradient over weight with bar, which is quantized weight, times SW to the power of -2. So similarly, we can do the same scaling factor correction for the bias. Just 2 terms, we merge them together as to the power of -2. Okay, so we rescale the gradient in this way. So SW is something smaller than 1, to the power of -2 is something much larger than 1. So the gradient becomes larger. So we can actually learn stuff. Previously, the gradient is too small. W over gradient is too large. You're not learning much. Large weight, super small gradient, you're not learning stuff. But here, we scaled up the gradient so that we can actually learn the stuff. As we expected, this is int8 plus quantization-aware scaling, int8 plus QAS. And as a result, the weight over gradient ratio can match the FP32 version, which was in blue versus in yellow. It's no longer in green. Okay, so we solve this problem, and we can observe as the training goes by, the training loss drops much better, much faster compared with without the quantization-aware scaling. So this is training epochs with the training loss, training epochs with the validation loss. This is without this quantization-aware scaling. This is with the quantization-aware scaling. Very effective method to reduce both the training loss and the activation loss. No hyperparameter tuning. You're just reusing the same scaling factor which we have derived during the inference lab. Just reuse this scaling factor and correct it. Okay, just 1 line of code to correct the gradient weight and also the gradient to the bias. And you can immediately observe better training curve and also recover the accuracy. Okay, so int8 SGD naive approach double-digit degradation with QAS, you can fully recover the accuracy. Some other approaches like Atom, remember it has 2 extra optimization states we have to save. Although it has a good accuracy, not as good, but it introduces 3x. The memory consumption is 3x because it introduced the 2x of optimization states. So summary so far in this lecture, the gradient is not safe to share. You can leak the information from the gradient, and staying local is very important. So on-device training is important. And CE's training memory bottleneck is actually the activation. So we have to think about techniques to reduce the activation during training. So bias only update and light residual technique in tiny TL, tiny transfer learning. Tiny TL can reduce the activation memory. And full update is just too expensive. There's opportunity for sparse update. Since not all layers are equal, we can intelligently find those salient layers to update. And also, why training a quantized model is just so difficult, and due to those mismatch of the scaling factor, and we can easily resolve that problem by quantization-aware scaling. So in the next lecture, we're going to learn how do we translate these algorithmic improvement into measured saving and speed up, and also talk about prompt tuning, and also some of the prompting and engineering efforts in the context of large language model and foundation models. All right, that's all for today's lecture. Thank you.